The sediments are now piled up on the flank of the mountain and ready to be transported towards their final destination, the sea. This is the distributor component of our source-to-sink system. Using the theoretical knowledge gathered in previous models, we will follow the path of these sediments and discuss the changes they experience during this trip down to the sink. Valleys in the high mountains are typically steep. Precipitations are erratic and characterized by relatively dry periods interrupted by brief but very intense precipitations. Change can occur on a seasonal basis, but also at longer wavelengths. During the periods of heavy precipitations, huge amounts of water will flow along the mountain flanks and reach the valley. Water level will rise, and because the section of the valley cannot increase, velocity becomes very high, and most sediments on the slope will be transported away. When precipitations go back to normal, waters will flow regularly, and clean sediments falling from the slopes, carrying away all the grains that can, and leaving behind only those which are too heavy. A short time after the storm, waters are clear. Away from the steep mountains, valleys become wider, and braided river systems develop, characterized by a network of anastomosing channels and large amounts of sediments dispersed on the valley floor. During periods of strong precipitation, the abundant and sediment-loaded rivers fill these wide valleys, rework a large portion of the sediments present, and deposit part of the load they have. In more quiet moments, waters will flow in anastomosing channels, removing all the sediments they can carry and leaving the rest behind. The waters are again clear, and channels do not change. Sediment deposit in braided system characterized by a complex architecture with coarse permeable lithologies intercalated with finer-grained, less permeable ones. Exploiting these reservoirs is challenging. A major change occurs when the river exits the steep part of the mountains and enters large valleys within the chain, or even the plains bordering the mountain themselves. At this transition, the slope of the river decreases substantially, and the section within the river can flow becomes very large. As a result, the rivers charged with water and sediments during periods of high precipitation experience a dramatic drop in velocity and correspondingly of carrying capacity, suddenly dumping most of the sediments they have. When floods pass, waters flow along non-perennial channels, locally cleaning the sediments. These systems are alluvial fans, sedimentary systems of great importance because on the whole they have large permeability and very advantageous for water and hydrocarbons. The cartoon you see in the slide provides a scheme for the understanding of sedimentary succession associated with alluvial fans. The fan has a triangular shape with the apex placed at the exit of the valley in the plain. From here, waters during normal precipitation period flow along distributor channels. Grain sizes change from the apex to the foot, being coarse-grained at the top and finer-grained at the bottom. Sorting is in general poor because sediments have been dumped in it quickly. In the vertical section, you can recognize the convex shape of the fan and the trace of distributed channels active during fair weather conditions. Having deposited most of the carried sediments in the alluvial fans, the rivers enter then larger and wider plains. Processes in deposit taking place here will be shown in the next video. Here we are in the large floodplains of the world. Large rivers often meander through the plains and once in a while experiencing major floods. A world of great historical importance. Some of the earliest civilizations developed along rivers, such as the Euphrates and the Nile. Having left the steep mountain valleys and having dumped sediments in building alluvial fans, rivers entered now gently sloping regions, forming braided river systems and eventually start meandering in large alluvial plains. Meanders are bends in the river course which form from small irregularities and progressively grow until the neck between the two meanders is broken and an oxbow lake detached from the main river is formed. The process controlling such migration is the lateral variation in river velocity, which is higher on the external side of the meander and low in the inner side. As a consequence of these changes, the river erodes the outer sides of the meander and deposits sands in the inner part, resulting in an outer migration of the meander. You can see the main components of the meandering system in this beautiful picture. In the slide, you see how a good overview of the processes taking place in the vertical dimensions within the river. In the external parts of the meander, water has high flow velocities and is therefore able to erode a significant amount of sediments. These sediments are transported and then deposited in the internal part of the following curve, where flow velocity and therefore carrying capacity are low. In a vertical section through the meander, you can see the effects. On the right-hand side, you can see the sediments being eroded. On the left-hand side, sediments are being deposited with beds inclined towards the riverbed. Sedimentary successions associated with meandering rivers are characterized by large bodies of sands within finer grained and more regular floodplain succession. The internal structure of the sand is characterized by facets, which are non-horizontal layers dipping towards the deeper part of the former riverbed. Because of their high sand content and associated high porosity and permeability, meandering river deposits are very interesting targets for water and hydrocarbon exploration. The challenge is, however, to predict their spatial distribution, as they are generally surrounded by finer grained, less permeable deposits. Once in a while, major floods occur. These are typically associated with increased precipitation on the mountains and possibly with difficulty in discharging waters to the sea. Floodplains are typically far away from the mountains, and the increased water volumes generated by high precipitation in the mountains arrive with a significant delay, but also last strong and last longer in the order of weeks. The magnitude or frequency of floods vary, but interesting enough, when plotted together on a logarithmic scale, fall along a straight line, which implies a strong correlation between the numerous small events and the few large ones. These curves are of crucial importance to estimate strength of river protection intervention. And here you see what happens during and after the flood. As valleys and the large plains have low depths, river level will rise with the flood, and waters will pass river banks and invade the floodplains. As soon as the waters get out of the riverbed, the flow velocity will dramatically decrease, and the sandy sediments they were carrying are dumped, forming natural dikes, which we call levees. Waters will then invade the large plains, but only carry the very fine-grained, silt to fine-grained sized sediments typical of floodplains. Once water discharge goes back to normal, waters in the plains will gradually infiltrate the ground and or evaporate, and the river will retain its normal flow. This is what floodplain deposits look like in the field: a regular succession of fine-grained sediments with horizontal and plane parallel overall stratification. You do not need to look very careful to detect a clear cyclic pattern with whitish layer regularly alternated with more reddish ones. There can be several reasons controlling these changes. A typical possibility is that of whitish layers corresponding to periods of erosion where coarser grains are sedimented. The bundles of more sandy layers can correspond to periods of increased flood intensity and magnitude. All these are climatic signals. And now we are at the end of the journey of the river, which formed as a small creek in the mountains and has now reached the coast. During this journey, sediments are being produced by erosion, transported and deposited. And as we have already mentioned in previous movies, the way these sediments are organized, that is, the facies, depends on the physical processes in the site of deposition. Their thickness, on the contrary, depends on the amount of substance affecting the same area. Floodplain deposits can be in places hundreds of meters thick. The rivers, which started from the mountains and have been flowing through the foothills, the alluvial plains, and the floodplains, have eventually reached the sea. The sediments they carry and which they will deposit in the marine environment have been mainly produced in the mountainous regions, have been substantially modified in amount and type during the course. The amount of sediments which reaches the sea depends on the amount of sediment produced in the source area and how much of this has been deposited in subsiding domains prior to reaching the sea. You can see that by far the largest amount of sediments is transported by the rivers draining the Himalayas. These mountains experience strong uplift, are affected by very strong precipitations, and are relatively close to the sea, decreasing the amount of sediment abandoned in the continent. Sediments are eventually brought to the sea. The type of sedimentary structure the rivers and the sediments they carry will form depends on what the river brings and, on the other side, on the processes taking place in the coastal domain. We will look in more detail into these processes during the next clip, but for the moment it is enough to consider in a qualitative sense waves, currents and tides. I'm sure all of you have at least a qualitative knowledge of these phenomena. We distinguish two end members, estuaries and deltas. Estuaries are semi-enclosed coastal bodies of water with free connection with the open sea and where seawater is measurably diluted with fresh water derived from land drainage. They typically form during the other glaciations when lower sea level activated erosion and the formation of valleys deeper than present sea level. Deltas are a landform which develops from the deposition of sediments carried by the river as the flow leaves its mouth and enters slow moving or standing water, typically the sea. Estuaries and deltas are an end member of a continuum. In general, deltas are favored by high sediment input and weak movements in the water column, which prevents sediments being transported away. Deltas play a major role in present-day coastal domain as well as in the geologic record. Because they are associated with large sediment input, deltas grow in size. As the incoming sediment cannot be stored above sea level, it will be transported and dumped in front of the delta slope. In a vertical section, you can see the results of such a delta growth. At each stage, coarse-grained sediments are dropped at the delta top, sands are deposited in layers dipping towards the sea, and silts and shale being deposited at the toe of the faucets. And now we really need to look at what is happening in the sea.